So, the next concept that we have to look is eigenvalues and eigenvectors of a second order tensor. Okay. So, for a given second order tensor A, can we say that there is a vector which gets mapped to itself or some factor of itself? So, if there is such a vector which exists, that vector is called a eigenvector, and the scalar multiple by which it is projected is called the eigenvalue. So, as you can see here, this equation a n equal to lambda n. Okay. So, here the second order tensor A is mapping this vector n to a scalar multiple of itself. Okay. Scalar multiple is lambda, and then you have n on the right hand side. Okay. So, this tensor A maps the vector to a vector which is along the direction of the vector itself. Okay. So, in this case n is called the eigenvector of A, and lambda, okay, is called the eigenvalue corresponding to the eigenvector n. Okay. So, how do you find the eigenvalues and eigenvectors of a second order tensor? Okay. So, this you can find using solving a third degree polynomial, which is also called the characteristic equation, and this characteristic equation is obtained when you take the determinant of a n minus lambda n and set it to equal to 0. Okay. So, if I write using matrix notation, this would be determinant of A into vector n minus lambda vector n equal to 0. Okay. So, this is just like your finding eigenvalues and eigenvectors of a matrix A. Okay. In the previous lectures, we saw that you can write a second order tensor as a 3 by 3 matrix. Okay. So, to find a eigenvalue and eigenvectors of a second order tensor, you have to first express that tensor as a 3 by 3 matrix, and then you have to find the eigenvalues and eigenvectors of the matrix. Now, there are special class of second order tensor which are symmetric, and symmetric tensors play a huge role in continuum mechanics. So, an important property for these symmetric tensors is that the eigenvalues of these tensors are real, okay, and that the corresponding eigenvectors are all orthogonal. Okay. So, this means that all lambda I are greater than equal to, okay, sorry, are greater than 0, they are real, okay, sorry, mod of, yes. So, they are all real numbers, and then ni dot nj, okay, if I is not equal to j will be delta ij, which means if I is equal to j, so n1 dot n1 will be equal to 1, because the eigenvalues are orthonormal, and then n1 dot n2 for example will be equal to 0, because their eigenvectors are orthogonal. Okay. So, the another important thing to note is this Cayley-Hamilton theorem. Okay. What it states is that a second order tensor satisfies its own characteristic equation, which is given by a cube minus I a is the first invariant of tensor A, times a square plus I2 into A, okay, I2 into A, so 2A. Okay. So, this 2A is your second invariant of the tensor A minus 3A into A. So, this 3A is basically third invariant, which is nothing but the determinant into A. So, a second order tensor will satisfy its own characteristic equation. Okay. This is called the Cayley-Hamilton theorem. Okay. So, once you have the eigenvalues and eigenvectors, you can express a symmetric tensor S in terms of its eigenvalues and eigenvectors, and this is called the spectral decomposition of the tensor, symmetric tensor S. Okay, and this is given by following equation. Okay, as you can see here, S is given by summation over I equal to 1 to 3 lambda I and I tensor product N I. Okay. Now, there are, you would notice that there are 3 i's here in this expression. Okay. So, we have to explicitly write no sum over I, because earlier when we are using indicial notation, we denoted that if the indices is repeated, a summation over is implied, but here we do not want summation. So, we have to explicitly write here no sum over I. Okay. So, for a second order tensor which is symmetric, the 3 invariants of a second order tensor can be written as in terms of the eigenvalues of the second order tensor S. So, the first invariant is nothing but the sum of the eigenvalues, the second invariant is nothing but the sum of square of the eigenvalues, and the third invariant is nothing but the product of the 3 eigenvalues. Okay. So, now suppose we want to show that indeed the first invariant of the tensor, symmetric tensor, is the sum of the eigenvalues. So, how can we show that? This we can show when you can start with the spectral decomposition expression. Okay. So, we start with the spectral decomposition of S and then we take trace on both the sides. Okay. So, now we have taken trace on both the sides. So, trace on the left hand side should be equal to trace of the right hand side. Now, we can take the trace inside the bracket, okay, that is here, and then we note that, and this property we discussed in the previous slides, that trace of A tensor product B, okay, will be equal to A dot B. Okay. So, here trace of Ni tensor product Ni will be Ni dot Ni. Okay. And we know from the property of eigenvectors of a symmetric tensor that the eigenvectors of a symmetric tensor are orthogonal and they are also orthonormal. So, Ni dot Ni will be equal to 1. Okay. Once you have trace of Ni tensor product Ni as 1, you are left with only summation over lambda i's, which is nothing but lambda 1 plus lambda 2 plus lambda 3, and that is what we wanted to show. Okay. So, similarly, you can show the other 2 expressions here. Okay. So, you start with the expression for second invariant and the third invariant, and you can definitely show that these properties hold. Okay. And these properties will be used later on during hyperelasticity. Okay. Next, we come to what is meant by volumetric and deviatoric tensors. Okay. So, every second order tensor A can be decomposed into a volumetric part, okay, which is also called the hydrostatic part or the spherical part, and a deviatoric part. Okay. So, as you can see here from this equation, a second order tensor A can be written as a volumetric part A subscript VOL, VOL stands for volumetric, and plus A subscript DEV, which is short for deviatoric. Okay. So, now the volumetric part is given by 1 by 3 trace of A into second order identity tensor, and then using this expression over here, we can get the expression for the deviatoric part, which is given by A minus the volumetric part. Okay. So, one thing to note is any tensor of the form alpha I, where alpha is a real number, will be a volumetric tensor or a hydrostatic tensor or a spherical tensor. Okay. So, some of the important properties of the volumetric and deviatoric tensors are given here. Okay. So, the trace of the deviatoric part of the tensor A will be equal to 0. Okay. So, this we can prove, suppose we want to prove. So, we can start from the expression. So, this is nothing but the deviatoric part of A if we take the trace, okay, trace of A deviatoric, okay, will be trace of A minus A volumetric, okay, which is nothing but trace of A minus trace of A volumetric, okay, where the volumetric part is 1 by 3 trace of A into I. Okay. Now, 1 by 3 and trace of A, these are scalar quantities, so they can be taken out. So, trace of A minus 1 by 3 trace of A into trace of second order identity tensor. So, what is the trace of second order identity tensor? That is nothing but it is equal to 3. Okay. So, you have 1 by 3 trace of A into 3 into trace of A. Okay. So, this 3 gets cancelled out and then this trace of A and trace of A cancels out, which gives you 0, and that is what we wanted to prove. Okay. Similarly, you can show the other two relations, okay, and this I leave it to you as a task. Okay. You can do it, and if you have any problem, as usual, you can always contact me. The next important concept is the concept of positive definite tensor. Okay. So, what is a positive definite tensor? So, a positive definite tensor is defined as one which satisfies the following relation. So, you are given a tensor A, and for any given vector V which is not equal to the 0 vector, if V dot A V, okay, is greater than 0, then that tensor A will be called a positive definite tensor. Okay. So, this quantity Q V is also called the quadratic form associated with the symmetric second order tensor A. Okay. Now, there can be other terminologies for the quadratic form Q V associated with the values of V dot A V. Okay. So, say V dot A V is greater than equal to 0. See, earlier it was only greater than 0. Now, if you allow also values to go to 0, okay, for all V's which are not equal to 0, then A will be called positive semi definite. Okay. Now, if V dot A V is less than equal to 0, okay, for all values of V which are not equal to 0 vector, then A is called the negative semi definite. And if V dot A V is always less than 0, whatever be the value of V, okay, then A is called the negative definite tensor. Okay. Okay. So, what are the conditions under which a tensor can be positive definite? So, I have stated 3 conditions here. The first one is the diagonal elements of A, that is the matrix formed by the second order tensor A, are all positive, they all should be positive. The largest element of A should lie along the diagonal of the matrix, and the determinant of A should be more than 0. Okay. If these properties are satisfied, then the tensor will be a positive definite. So, you need not do all the way V dot A V. If these 3 properties hold, then that tensor will be a positive definite tensor. Okay. A necessary and sufficient condition for a symmetric tensor to be positive definite is that all its eigenvalues are positive. Okay. As you can see here, all the eigenvalues have to be positive. Okay. They have to be real and they have to be positive. Okay. Now, your task is to show that this statement, that the for a symmetric second order tensor to be positive definite, all its eigenvalues are greater than 0. You have to prove that statement, and I have provided hint also. So, again you try it yourself, and if you have any problem you can always contact me and I will give you some hints on how to solve this. So, written here you have to start from the spectral decomposition of a second order tensor. You can also look into some linear algebra book, because a second order tensor can be written as a 3 by 3 matrix. So, it also implies that for a symmetric matrix its eigenvalues are always greater than 0. Okay. So, in linear algebra book you can find this proof. The same proof applies for a symmetric second order tensor. Okay. Now, we come to leave second order tensor, now we come to higher order tensor. So, okay, before we go to fourth order tensor, it is good that we spend some time with what are called the third order tensor. We will not encounter third order tensor much, but before making the jump from a second order tensor to a fourth order tensor, definitely there will be a question, are there some third order tensor. So, we will discuss this. So, a third order tensor is defined as a linear mapping from an arbitrary vector u to a second order tensor v. Okay. So, you see the symbol here, okay, it is a calligraphic A, okay, that is how you we represent higher order tensors. Third order or fourth order, we will use the calligraphic bold symbol. Okay. So, when we are writing, we will always write A and then we will put 3 underbars, that is how I prefer. You put 3 underbars to show that it is a third order tensor. So, A u is equal to B. Okay. So, a third order tensor operates on a vector and gives you a second order tensor. Okay. So, just like a second order tensor operated on a vector to give you another vector, a third order tensor operates on a vector to give you a second order tensor. So, in indicial notation, this we can write as A I j k u k equal to B I j. Okay. Now, a third order tensor can also be obtained using the tensor product of 3 vectors. Say you have 3 vectors u, v and w. So, if you take u tensor product v tensor product w, so the resultant quantity that you get is a third order tensor A. Okay. And the way it functions is, if you take an arbitrary vector x, then u tensor product v tensor product w operating on x is defined as w dot x into u tensor product v. Okay. So, there are other ways to obtain a third order tensor. So, one way is you take the tensor product of a vector with a second order tensor, u tensor product A gives you a third order tensor A, tensor product of a second order tensor A with vector u again gives you a second order tensor, a third order tensor A. Okay. So, some of the properties of a third order tensor are mentioned here, okay, and this you can show it yourself. Okay. So, you have to remember these properties. Now, just like we had defined basis for vectors and second order tensor, similarly a basis for a third order tensor is the tensor product of the base vectors E I, E j, E k, okay, and it is written here. A third order tensor A will be triple summation over I j k, A I j k, E I tensor product E j tensor product E k, okay, where the component of this tensor A, that is A I j k, can be obtained by following relation. Okay. E I tensor product E j double contraction with A E k. Okay. Now, you can show this also, it is not very difficult. Just notice that I j k in this expression are free indices. So, all you need to do is substitute this expression of A here, and then instead of using I j k in this expression, just use some other symbol, say L, M and N. Okay. So, all you need to do is start from EI tensor product EJ, double contraction with summation over L M N A L M N EL tensor product EM tensor product EN operating on EK. Okay. And then you use the properties which are mentioned in the previous slides, and you can simply show that you will get A I J K. Okay. So, one of the examples of a second order or a third order tensor is the alternating tensor E. Okay. That is your permutation symbol. So, epsilon I j k is given by EI dot E j tensor product E k. Okay. This also again you can show, we already had discussed. Okay. How to get the component of our third order tensor? You can use the expression and show that indeed epsilon I j k is EI dot E j tensor E k. Okay. Now, the trouble contraction that we defined between two second order tensor, you can recall that A tensor product B was A I j B I j. That is how a second order, the double contraction between two second order tensors was defined. Similarly, we can extend the definition to higher order tensor. So, for example, a third order tensor double contracted with a dyad U tensor product V will be nothing but A V into U. Okay. So, this you can easily show. I will write using index notation to be very fast. A I j k U j V k, okay, which is nothing but A I j k V k U j. Okay. And this is nothing but indirect notation A V into U, okay, which is the right hand side. Similarly, there are other properties associated with the double contraction applied to third order tensor and are mentioned here. You can obviously prove them using indicial notation or using operational approach. Next, we move to what are called fourth order tensor. Okay. So, a fourth order tensor will operate on a vector to give you what is called a third order tensor. Okay. So, notice, let calligraphic C, that bold calligraphic C here represents a fourth order tensor. It operates on a vector U and it gives you a third order tensor A. So, in indicial notation I can write C I j k l U L equal to A I j k. Okay. So, note that we do not make any explicit difference between third order or fourth order tensor. Okay. They are both written in the same way, and then from the context of your problem you will be able to judge which one is the fourth order tensor, which one is the third order tensor. So, at this stage there should not be any confusion. Okay. You will know from the context of your problem. Now, as was in the case for a second order tensor and third order tensor, you can take the dyadic of a 4 vectors to get a fourth order tensor. So, if you have vectors u, v, w and x, so the tensor product of u with v, v with w and w with x. So, u tensor product v, tensor product w, tensor product x. This will give you a fourth order tensor C. Okay. And when this C operates on a vector, okay, from the definition it should give you a third order tensor. So, u tensor product v, tensor product w, tensor product x operating on v will be x dot y and u tensor product v, tensor product w. Okay. So, there are some other definitions of fourth order tensor that can be obtained as tensor product. So, you can take tensor product of a third order tensor with a vector to get a fourth order tensor, and this when operates on a vector v will give you u dot v into the third order tensor A. Okay. So, tensor product of a vector with a third order tensor also gives you a fourth order tensor, and tensor product of two second order tensor gives you a fourth order tensor. Okay. Now, the double contraction between a fourth order tensor and a second order tensor. Okay. So, a second order tensor, say a dyad U tensor product V, and C is the fourth order tensor. So, the double contraction, the way it is defined is C double contracted with U tensor product V will be equal to C V into U. So, in initial notation, the way I will write is C I J K L, 4 indices because it is a fourth order tensor, and because there is a double contraction, the last two indices K and L will be same for the next second order tensor, which will be U K V L. Okay. So, this is nothing but C I J K L V L U K, and this is in direct notation C V. Notice I have put 4 underbars U 1, okay, U 1 underbar. Okay. So, that is how you can show. So, example of this relation, okay, this property is this relation over here, where the stress tensor, Cauchy stress tensor can be obtained as double contraction of the fourth order material constitutive tensor C with the strain tensor. Okay. That is where this double contraction of a fourth order tensor with a second order tensor comes. Okay. Now, there are certain properties of double contraction associated with fourth order tensor, and this we have listed here. Okay. So, you can again use the indicial notation, you can use operational approach to verify each and every one of them, and I strongly suggest that you try these yourself. It will give you a lot of practice, and if you have any problem, please do not hesitate to contact me. Okay. So, now as was with the case with second order tensors and third order tensors, there is indeed a basis for fourth order tensor, and this is obtained by taking the tensor product of the basis vectors E I, E j, E k, E l, okay, where I, j, k, l will be going from 1 to 3, and corresponding to each basis you will have a component which is C I j k l. Okay. So, in total there will be 81 such components, okay, because at each place each indices can have 3 options. So, 3 into 3 into 3 into 3 total, that is 81. So, there are 81 components of a general fourth order tensor, and you can get the component of a fourth order tensor by using this relation over here. Okay. C I j k l is E I tensor product E j double contracted with the fourth order tensor C double contracted with E k tensor product E l. Okay. Now, there are 2 specific examples of fourth order tensor which are of much use. Okay. They are fourth order identity tensor. What is a fourth order identity tensor? It is denoted by this calligraphic bold I. This fourth order identity tensor, when contracted with double contracted with a second order tensor S, will give you the second order tensor S itself. Okay. That is the property of fourth order identity tensor. Okay. Once you have this property and you know this relation over here, okay, this relation, you can get the components of this fourth order identity tensor. Okay. So, this is the relation. Instead of C here, you just substitute the fourth order identity tensor, and then you can use this property that I contracted with E k tensor product E l will give you nothing but E k tensor product E l, and then you have E I tensor product E j, okay, double contracted with EK tensor product EL. Okay. And what is that? That is EI dot EK EJ dot EL. Okay. EI dot EK is nothing but delta IK, and EJ dot EL will be delta JL. Okay. So, the components of fourth order identity tensor is delta IK, delta JL. Similarly, there is fourth order transposition tensor, which is I tilde here, and when it double contracts with S, it gives you the transpose of the tensor. Okay. And the components of this transposition tensor here I tilde IJKL is nothing but delta IL delta JK. Okay. So, once you have these components, okay, if we go to our previous slides. So, this is IJKL, the component delta IK delta JL. Now, this if you substitute, okay, if you substitute here in this expression, then the fourth order identity tensor can be written as summation over I j from 1 to 3 EI tensor product EJ tensor product EI tensor product J. Okay. This is very simple to show. Similarly, the basis for a fourth order transposition tensor will be EI tensor EJ tensor product EJ tensor product EI. Okay. Now, you can show that both of these fourth order identity tensor, which is the identity tensor and the transposition tensors, are isotropic tensor. So, as you would remember, an isotropic tensor is one whose component do not change with the change in the basis. Okay. Once you rotate the basis or your coordinate system, then the component of the tensors do not change. Okay. So, what you have to do is write these relations over here in the prime basis, and then because EI, EJ, EK, EL are given to be base vector, you know the relation between EI dash and EI. Okay. Use this in expressions over here, and then you can show that the component of say identity tensor in the prime basis and the unprimed basis are both same. Okay. So, the most general form of a fourth order isotropic tensor can be obtained as scalar multiple of the tensor product of second order identity tensor plus fourth order identity tensor and fourth order transposition tensor. Okay. So, C will be alpha I tensor product I plus beta I plus gamma I tilde. So, what is this, why this tensor is important? It is important because fourth order identity tensors are of great importance in continuum mechanics, because they will be used to describe the elasticity tensor of materials that exhibit same property in all the directions. Okay. So, if you want to represent properties of a material which has same property in all the direction, then the most general form for that fourth order tensor will be this isotropic tensor given by expression over here. Thank you.